Object-relational mapping is a great technology. Once you get used to it, you'll never want to go back to CLI like JDBC. However, it does have a learning curve, and the learning curve mostly involves mapping classes to tables. So in the second part of the lesson, we'll focus on how to use JPA annotations to do the mapping. But first, let's see how to use this utility called schema export. It's a class provided by the Hibernate library, and it can use the mapping annotations to generate SQL create table statements. Here, for example, I have my employee class properly mapped, and here is the utility called schema export. And if we run this, it asks for a command line parameter that output the SQL statements. So let's do that by editing the run configuration. So I'm going to call this run configuration, let's say Hibernate HBM to DDL, and to give it a command line argument for the output file. So let's say I want to output to the file under project location, and then /source/main/scripts, and then I'll call the file Hibernate examples.ddl. Apply run, and run. Yeah. Because I used project location, I have to select a project before I can run it. Okay, so it's supposed to generate a new file called hibernate-examples.ddl under scripts. So let's refresh, and that file is now indeed here. If we look at this file, we can see that this is the SQL statements generated by schema export based on our annotations for employees. We can see that this employee class is going to be mapped to an employees table, and in addition to the table, it also has the foreign key constraint that specifies supervisor ID. The foreign key references back to the ID of the employees table, and it also creates a sequence called the Hibernate sequence, and this is how PostgreSQL can generate unique new object IDs, and those IDs are generated from this sequence, Hibernate sequence. So basically, after you've done the mapping, you can run this tool to check if the database tables will be what you expect. And I think this is particularly useful for JPA and Hibernate beginners. Oftentimes, you are not quite sure whether your annotations are correct. Then run this and check if it can generate the right tables. Okay, so moving on to actual mapping. Here are some basic annotations used for mapping, and we've seen most of them in the first part of the class. We've seen entity, which we need to use to annotate a persistent class. Table can be used to customize the tables this class is mapped to. ID is, of course, for the special ID field, and generated value is for automatically generating new unique IDs. And for fields of simple types like numbers and strings, we can use the basic annotation, and this annotation can often be omitted, and we can customize the columns mapped from these fields using the column annotation. And for class types, we can use many-to-one, or one-to-many, or many-to-many, and one-to-one. Also note that generally speaking, there are two types of annotations here. Most of these annotations are used to describe the classes on the application side. Some annotations, for example, table and column annotations, are used to customize the tables on the database side. We have talked about basic mapping in the employee example in the first part of the lesson. Here we'll talk about mapping some additional things, specifically embedded class, collection, and inheritance. Embedded class is the easiest one, and this is probably the most commonly used example for embedded class. Suppose we want to store user information like ID, username, address, and so on. In application design, it usually makes sense to package the components of an address like street, city, state, and zip code into a separate class. It just looks cleaner this way. However, if each user only has one address, in the database, it would be more efficient to store address information in the users table so we can avoid unnecessary drawing. In this case, we can annotate the address class as embeddable and the address field in the user class as embedded. The result is that the address class won't have its own table, and all the address columns will be embedded in the users table like this. And this way, both the application designer and the database designer will be happy. Collections are a bit more complicated. Let's start with a relatively simple case where the collection is a collection of simple types like string and numbers. In this example, I have a customer class. Each customer has an ID, name, address, and we also store the customer's phone numbers. Supposedly, a customer could have several phones, like home phone, office phone, cell phone, and so on. So it's going to be a set of strings. In JPA, a collection of simple type is called an element collection. And with this annotation, the customer class will be mapped to two tables. The phones will be stored in a separate table with a foreign key column references the main customer's table. So let's see how it looks. I have my customer class here, and let's put in the annotations that we're familiar with. So it should be an entity, and I want a table called customers, and ID field should be annotated with ID, and we want to automatically generate new unique IDs, so it's generated value. And the string is a simple type field, so we can omit that. Same for address, and then we have the set of phones. And as I mentioned here, we can use annotation called element collection to annotate this. So let's run our HBM to DDL, and let's check this file. Notice that now, in addition to this employees table, we now have two new tables. One is called customers with ID, address, name, and the other one is called customer underscore phones, and that is the table for the phones. So notice that the default name used by the ORM tool here is class name, and then property name. Property is this one for the table name, and for the foreign key column is again class name and underscore ID, and for the phones column is the property name, again is this property name. Now, if you don't like this default names, and I really don't like them because they don't follow SQL naming conventions, you can customize this table by using a collection table annotation. So using this annotation, we can change the table name, we can change the foreign key column name, and we can also change the name for the column that actually store the phone values. So let's grab this and let's put it in here. So the table is going to be called customer phones with lowercase c, and foreign key column is going to have lowercase c as well, and the phone column is called phone instead of phones because column name should be singular. And let's import this one and run this again. Okay, so now this table looks much better. Okay, there are two commonly used collection types, set and list. Going from set, like here, to list is a little bit tricky. Most people know that the main difference between a set and a list is that elements in a list are ordered, while elements in a set are not. What most people tend to forget is that rows in a table are actually not ordered either. This is not very intuitive because when you look at a table, you'll see first row, second row, and so on, and you'll think that there's an order there. But the relational model says that there is no guarantee the results of a query will be in a certain order unless you use an order by clause. What this means is that when you map a list to a database, you need to do a little extra work. So suppose, for example, instead of set of phones, we change it to list of phones. And there are two ways to enforce an order on the rows in a table. The first is to use the natural order of an existing column. For example, suppose we always want to list the phones in alphabetic order. Then we just need to say order by phone when we load the phones from the database into a Java list, and that's it. For example, here, the phones can be stored in this table, and the customer's phones will be in this order with the 2, 3, 2, 3 numbers first, and 1, 2, 3, 4 of course goes before 6, 7, 8, 9, and then followed by the 6, 2, 6 number. And it's ordered by alphabetic order of the phone itself. However, sometimes natural order may not be the order you want. For example, what if we want to list the phones in this order? First, this 323 number, and then this 626 number, and then the other 323 number. In this case, we can no longer rely on the natural order, so we have to use an extra column. This column basically keeps the index of the elements in the list. For example, the 1, 2, 3, 4 number is the first one in the list, so it's going to have an index of 1, and the value for this column is, the index for the first one is 0, so the value for this column is going to be 0. And this phone is the second one in the list, so the index is 1, and that's the value for this column, and so on. So once we understand this, it's easy to understand the annotations. So corresponding to these two types of ordering, there are two annotations to use. Order by annotation typically takes the form of order by and property name, and then either ascending or descending. For simple types like string, there's no properties, so it's just ascending or descending. And if you want to specify order that is not a natural order of an existing column, then of course you can use order column, and the ORM tool will look for an actual column in the table. So let's try this one here. I'm going to change set of I'm going to change phones from set of string to list of string. And I'm going to use order column here, and the name of that order column, we'll call it phone order. And if we run HBM to DDL, we can see that now this table has an actual column called phone order, and just like what we show here. Okay, moving on from collection of simple types to collection of object types. And there are several things I'd like to discuss. Relationships, which are also called associations in Hibernate and JPA literature, and the unidirectional and bidirectional association, the pros and cons, and something called cascading behavior. The first and also the most important is to correctly identify the type of relationship. You should have learned this in a database class, so here we just quickly review the key points. There are 4 types of relationships: many to many, many to one, one to many, and one to one. Many to one and one to many are the same thing, depending on which direction you look. In a many-to-many relationship, each entity in the first entity set can be related to many entities in the second entity set. For example, this one can be related to multiple on the other side, and this one can be related to multiple on the other side, and so on. And also, each entity in this set can be related to many in this set. So for example, this one can be related to many, this one can be related to many, and so on. I use the terms entity and entity set here because the concepts come from entity relationship modeling or ER modeling. You can use object and class instead of entity and entity set, and they basically mean the same thing. The key in determining the correct relationship type is to check both sides, from left to right, and then from right to left. If you check only one side, it's very easy to mistake this, for example, as a many-to-one or one-to-many relationship. For example, if you only check from left to right, but don't check from right to left, and then you may think that this is a one-to-many relationship, when in fact it should be many-to-many. And this is the many-to-one relationship. Again, if you only check one side, it's very easy to mistake it as a many-to-many or one-to-one. For example, if you only check from left to right, you will see that each entity can be related to 1 on the right, each can be related to 1, and you would think that, okay, it's 1-to-1 because it's the same as this one. But no, it's not 1-to-1 because you have to check from right to left as well. On the from right to left, this is one and many and one and many. So combining these two together, this is a many-to-one relationship. It's also called a one-to-many if you look from the other direction. And of course, this is one-to-one, and in this case, in both directions is one and one and one and one. Okay, so now let's add an account class to our customer example. Our assumption is that a customer may own multiple accounts and an account can only have one owner. Note that on one side is one many and on the other side is one one. So this is a many-to-one / one-to-many relationship between customer and the account. On the database side, the relationship is pretty clear, but on the application side, it's a little tricky. It turns out that there are several different class designs that represent the same relationship. First, we can have an owner in account class and a set of accounts in the customer class, and this is called a bidirectional association. We could also have only a set of accounts in customer, but no owner in account, or we can have owner in account, but no set of accounts in the customer class. And these two cases are called unidirectional associations. There are three questions we need to answer regarding unidirectional and bidirectional associations. First, do they result in different database schemas? The answer is no, because they all represent the same many-to-one / one-to-many relationship, so they map to the same database schema. If you are familiar with database design, you know that they all result in the same two tables, an accounts table and a customers table, where the accounts table has a foreign key column customer ID that references the customers table. So if they are all the same on the database side, does it make any difference on the application side? The answer is yes, indeed. Consider the two scenarios. Given an account object to find its owner and given a customer object to find the accounts owned by that customer. So let's consider these two scenarios. Given account A, find the owner of the account, and given customer C, find the accounts owned by this customer. Okay, suppose we want to do these two things, and if we take the first design, the bidirectional design, what we can do is this. If we are given a count, which is this one, and to find its owner, we can simply do a get owner, right? It's pretty simple. And similarly, for this scenario, given a customer and find the accounts, and because in this design, customer has a set of accounts in the customer class, so to get the accounts owned by the customer, we simply do get accounts, and that's it. Nice and simple. So what if instead of this design, we actually use a second design where we have the accounts in customer but no owner in account? Well, here, given a customer, find the accounts owned by this customer is still simple. So for the second design, it's still get accounts, and that's it. Get accounts. That's it. However, here it's no longer that easy because this account class doesn't have a reference to the customer. So how do we do this? Well, if you remember the queries we talked, the JPQL and the HQL queries we talked about in the first part of the class, you know that you can do something like this. We want to select from the customer class, and this customer class needs to join its own account set, and the account set, inside the account set, one of the account is this account. So in other words, without a reference to the owner in the account class, in order to get the owner of this account based on an account object, what we need is to write a query that looks like this, and then we pass the account object A to this query parameter, and this query will return the customer object that is the owner of this account. So in other words, not as simple as this, still doable, but we have to write a query. So let's say we use the third design. For the third design, given account, getting the owner is simple because we have the owner reference here, so this would be simply a get owner. But given the owner, getting the accounts is no longer as simple as calling a method. So again, it requires a query, and this query is slightly simpler than this one. At least it doesn't require a join. So it's something like from account, where owner is owner, and we can pass this customer C object to the owner query parameter, and this query will return all the accounts owned by this customer. So as you can see, from the application side, bidirectional association is, generally speaking, more convenient. In particular, when your application has to handle both cases. Of course, if one of these scenarios never happen in our application, then a unidirectional association would work just fine. So if this is the case, and if bidirectional association is much more convenient than unidirectional association on the application side, then shall we always use bidirectional association? The answer is almost yes, with an important exception when the collection is a so-called indexed collection, or in other words, when the collection is a list with an order column. We don't have time to get into the details. If you are interested, please check out the Hibernate documentation. Basically, for index collections, bidirectional association is rather tricky because it's difficult to keep the information symmetric in both classes. If you want to see an example of a bidirectional association with an index collection, check out the answer sheet and answer section class in the CSNS2 project. Again, once we understand the concepts, the annotations are pretty easy to use. Here is how we can map bidirectional association between account and customer. On the account side, it's many accounts belongs to one customer, so it's many to one. And on the customer side, it's one customer owns many accounts, so it's one to many. We need to use a map by attribute here to indicate that these two annotations actually refer to the same relationship. Note that the value of the map by attribute is a property name. Basically, it says that this association is already mapped by the owner property, which is this one, in the account class, which is specified here. So, knowing what we know, let's get back to our example and see how it looks. We already have our customer class here, and let's say we add, actually let's add the account class first. So for account class, we have entity, we have table, name is accounts, and ID generated value, and the balance we'll leave it as is, created on. To conform with SQL naming convention, I'm going to change the column name from created on to created underscore on. And the customer, as we mentioned here, is going to be many to one. And on the customer side, we can add a set of accounts, and this one is going to be one to many, and is mapped by the owner property in the account class. And let's add a pair of getters and setters. Where is it? Yeah. Okay. So let's run HBM to DDL again. And if we look at this, we can see that we now have a new table called accounts, ID balance created on, and the owner ID, and the owner ID is a foreign key, references customer, which is exactly what the table should be. And just like in the case of element collections, we can change set to a list, and we can use created on property to list all the accounts by the time when the account was created. And so using order by, we can easily change set to a list. Notice that because this list does not use an order column, it uses a natural order of existing column. It doesn't use a actual order column. This is not considered indexed collection. This is not considered an indexed collection, so there's no need to change this bidirectional association. And we can extend the example to many, basically allowing an account to have multiple owners. The annotations would be very similar to before, except of course many to one and one to many become many to many and many to many, and we still have the mapped by to indicate that these to many relationships mean the same relationship. And again, like for element collections, we can use additional annotation to customize the drawing table so that the drawing table would have the name, table name and column names that we like. Okay, let's talk about cascading behavior. What cascading behavior means is this. For example, suppose we have a customer coming to a bank to open 2 accounts. We can imagine that the bank computer system would do something like this. It would first create a new customer object, and then two account objects, and then add the two account objects to the customer object, and then save the customer object. Cascading behavior determines whether this save operation performed on the customer object should be cascaded to the accounts objects. There are, of course, other operations that could also be cascaded. For example, suppose at some point we want to remove this customer. Then we need to decide whether the remove operation should be cascaded to the accounts objects. Maybe it should, or maybe we want to keep the accounts and simply set their owners to null. So as you can see, it's not always cascading to the accounts objects or cascading to the children objects. Depending on the application scenario, we may or may not cascade that particular operation. There are several cascade types in JPA that you can use to specify which operations should be cascaded. There's detach, merge, persist, refresh, remove, and then you can say all operations, all of above should be cascaded. And this is how we can specify cascading behavior. For example, you can say only persist operation should be cascaded, or both persist and merge should be cascaded, or all operations should be cascaded. Usually persist plus merge is a safe choice because oftentimes you don't want to cascade the remove operation, which would be included if you say all. By the way, the default cascading behavior is not to cascade anything, so oftentimes during homework people will write code like this and ask a question, why my accounts objects were not saved to the database? Well, that's because by default none of those operations were cascaded. So if you want to save those accounts objects when you save this customer object, you have to say cascade, persist, and merge, or at least one of them, depending on whichever one you use to save the customer object. The last topic about mapping I want to discuss is inheritance. Inheritance is an important part of object-oriented design, but there's no inheritance in the relational model. How do we map superclasses and subclasses then? For example, suppose I want to create a new account type, CD account. For the sake of simplicity, let's say that a CD account is the same as a regular or a checking account, except that it has an additional field term. Term can be 30 days or 60 days or so, whatever number of days, which is the mature term of the CD account, and we'll use an integer to keep the number of days. Now the question is, how do we map the account class and the subclass CD account to database tables? It turns out that there are several ways to do it. First, we can store all the regular accounts and the CD accounts in the same table. Note that this table has all the columns of both regular and CD accounts. And for regular accounts, the value for the term column is going to be null, and that's okay. And because this table has different types of accounts, we'll need to use an extra column to tell them apart. And this column is called a discriminator column. The everything in one table approach is called single table inheritance strategy in JPA. In the superclass, we need to specify a discriminator column, and for each class, we need to specify a discriminator value, which will be used by the ORM tool to determine which record in the table corresponds to which class. So let's see how this one looks like. We already have our account here, and let's add this CD account. So we're going to make CD account entity as well, and notice that this CD account is a subclass of account, and it has a discriminator. Okay, yes. And this CD account has this extra column. And in the super class, we need to specify a few things. So we need to specify an inheritance strategy, and here it says single table. And we need to have an actual column, the discriminator column, and this is what the column will be called. And for regular accounts, we'll use the value checking as the discriminator value for regular accounts as opposed to CD for CD accounts. And inheritance type, let me import inheritance type. Okay, so now we have superclass and subclass, and let's run HBM2DDL again, and let's see. Okay, so now if we look at our accounts table, we can see that we have now an extra column here for term, and we also have an extra column here, the discriminator column account type. And if we scroll down, we can see that there are no table for CD accounts because all CD accounts will be stored in the same table. Okay, so this is one way of mapping superclass and its subclasses, and there's another way. So in this approach, all the common columns are stored in one table, and the actual fields of a subclass will be stored in a separate table. For example, suppose we have a CD account, then the ID, balance, and the created on fields of the CD account will be stored in the accounts table together with all the information of the regular accounts, and the term information of the CD account will be stored in the CD accounts table. If we want to retrieve the information of a CD account, we must combine the information from both tables because some of the information of that CD account is in this table and only the term information is in this table. And we know that in order to get the information for a CD account, we have to do join. So as you would expect, in JPA, if you take this approach, it's called the joint inheritance strategy. So for example, if we choose this strategy, instead of the single table strategy, we can get rid of discriminator column and value, and then change this one to joint. And in this case, we need to specify a table for CD accounts because we need a table here. So CD accounts will become like this. Oh, by the way, when you import when you import certain annotations, for example, table annotation, notice that there are two table annotations, one from JPA in the package javax.persistence, and one from the Hibernate library under org.hibernate.annotation. Always choose the one from JPA, or in other words, always choose the one from the javax.persistence class. If you mix annotations from two different places, for example, if you use some JPA annotation and then some Hibernate annotation, sometimes weird things would happen. So be careful when you import annotation, and if you have two options, always choose the one that says javax.persistence. So run this again, and now we can see that it results in two tables, the accounts table and then the CD accounts table. And CD accounts table has a term, and accounts table have all the other columns that's shared by both accounts and CD accounts. And there's yet another way to map superclasses and subclasses. In this approach, we simply treat a subclass as a standalone class, in the sense that it will be mapped to its own table with all the fields, including the fields it inherits from the superclass. So effectively, each class will have its own table, just like those are two different classes. In JPA, this inheritance approach is called table per class inheritance strategy, with this annotation, specify strategy, and then same thing, you need to specify a different table because there's a different table here. So just like choosing between bidirectional association and unidirectional association, when you try to map superclasses and subclasses, which inheritance type should we choose? Well, it really depends on what type of queries you need to support, and whether you are comfortable giving up some data integrity constraint for better performance. As our exercise, try the following two queries under the three different schemas. This one, and this one, and this one. Under those three different schemas, try to write queries for these two, and see which one give you more efficient queries. I can tell you the answer, and the answer is the single table approach provides the best performance. But the downside of that approach is that, as we mentioned, for this particular example, all the regular accounts will have nulls in the terms table, and you can imagine that if you map multiple subclasses into the same table, then there will be lots of nulls in the table, and it makes creating data integrity constraints much more difficult and sometimes not even possible. With that being said, it does give the best performance because you don't have to do drawing, and you don't have to do union. So the single table strategy is a strategy that usually gives the best performance. And if you don't care too much about data integrity constraints, and if you don't know which one to choose, then choose a single table approach. In fact, the single table strategy is the default strategy for inheritance in JPA. So this is about it regarding mapping using annotations. It's important to understand that JPA and Hibernate are development tools, not design tools. meaning that it's a way to express your design and automate the conversion between objects and the rows and columns, but they really do not do the design for you. To use ORM effectively, you should have a good understanding of both relational and object-oriented design. And here are some additional readings. The Pro JPA 2 book is a very good book, and you can check out the top link JPA annotation reference when you do your mappings. Although it says top link, it actually works for Hibernate just fine, and that's a good thing about using JPA.